Studies Section 6. Hypothesis Testing. Introduction. In this section, we will explore hypothesis testing. In doing so, we will analyze null hypothesis and alternative hypothesis. We will also discuss prediction problems, learning outcomes. When you have studied this section, you should be able to differentiate between null hypothesis and alternative hypothesis. Discuss the two types of prediction problems. Hypothesis testing. The procedures of hypothesis testing compare a conjecture of a population to the information contained in the sample data. Hypotheses are formed about economic behavior in the case of economic and statistical model. These hypotheses are then represented as statements about model parameters. Thus, hypothesis tests use the information about parameter that is contained in a sample of data, its least squares point estimate, and its standard error to draw a conclusion about the hypothesis. In every hypothesis test, there must be 1. A null hypothesis H0, 2. An alternative hypothesis HI, 3. A test statistic, 4. A rejection region, and 5. Conclusion. The null hypothesis H0. A null hypothesis is the belief or assertion that will be maintained until it is proved otherwise through scientific evidence. In this case, we reject the null hypothesis. The null hypothesis specifies a value for a regression parameter, which for generality we denote as beta x for k is equal to 1 or 2. We can state the null hypothesis as H0 such that Bx is equal to C, equation 80, where C is a constant and is an important value in the context of a specific regression model. The alternative hypothesis H1. This is paired with every null hypothesis, which is logical alternative hypothesis H1, that will be accepted if the null hypothesis is rejected. There is some flexibility in the alternative hypothesis, and it depends on some economic theory. For the null hypothesis H0 such that Bx is equal to C, the following are the three possibilities of an alternative hypothesis. 1. H1 such that beta x is greater than C. This is a situation where we reject the null hypothesis that beta x is equal to C and accept the conclusion that beta x is greater than C. The inequality alternative hypotheses are widely used in economics because economic theory frequently provides information about the signs of relationships between variables. 2. H1 such that beta x is less than C. Here, rejecting the null hypothesis that beta x is equal to C leads us to accepting the conclusion that beta x is greater than C. 3. H1 such that beta x is not equal to C. Rejecting the null hypothesis that beta x is equal to C would lead us to accepting the conclusion that beta x takes a value either larger or smaller than C. The text statistic. The null hypothesis sample information is contained in the sample value of a text statistic. It is the value of this text statistic that will enable us to decide either to reject or accept the null hypothesis. A test statistic has a special characteristic. Its probability distribution is completely known when the null hypothesis is true, and it has some other distribution if the null hypothesis is not true. Given that T is equal to beta x cap minus beta x over SE at the standard error into brackets beta x cap If the null hypothesis H0 such that beta x is equal to C is true, then we can substitute C for beta x, and it follows that T is equal to beta x cap minus C over standard error into bracket beta x cap bracket closed, equation 81. If the null hypothesis is not true, then the t statistic in equation 81 does not have a t distribution n minus 2 degree of freedom. The rejection region. This consists of values that are unlikely and have low probability of occurring when the null hypothesis is true. The logic is that if a value of the test statistic is obtained that falls in a region of low probability, then it is unlikely that the test statistic has assumed distribution, and thus it is unlikely that the null hypothesis is true, and then values of the test statistic will tend to be unusually large or small. The terms large and small are determined by choosing a probability alpha, which is called the level of significance of the test that provides a meaning for an unlikely event. The level of significance of a test alpha is usually chosen to be 0.01, 0.05, or 0.10. If one rejects the null hypothesis when it is true, then type 1 error has been committed, while if one does not reject a null hypothesis that is false, then type 2 error has been committed. Hill, Griffith, and Lin, 2006, argue that in a real world, we cannot control or calculate the probability of the type 2 error since it depends on the unknown true parameter beta x. The conclusion should state after the CAM test of the hypothesis is completing. It is the standard practice to conclude in terms of the economic implications of the findings because the statistical procedures are not ends in themselves. Rejection regions for specific alternatives. This section presents the nature of the rejection rules for each of the three possible alternatives to the null hypothesis H0 such that B beta x is equal to C. To have a rejection region for a null hypothesis, there is need for a test statistics which is in equation 81. Also, alternative specification is needed such as beta x greater than C, beta x less than C, or beta x is not equal to C. Third, there is need to specify the level of significance of the test. The level of significance of test alpha is the probability that we reject the null hypothesis when it is actually true, which is called a type 1 error. 1. One-tailed test with alternative greater than. When testing the null hypothesis H0 such that beta x is C, if the alternative hypothesis H1 such that beta x is greater than C is true, then the value of the t statistic tends to become larger than usual for the t distribution. We will reject the null hypothesis if the test statistic is larger than the critical value for the level of significance alpha. The critical value that leaves probability alpha in the right tail is the 1 minus alpha into bracket confidence interval. The rejection rules state that reject the null hypothesis and accept the alternative hypothesis if t is greater than or equal to t, bracket opened, 1 minus alpha, comma, capital N minus 2, bracket closed. The test is called a one-tailed test because unlikely values of the t statistic fall only in one tail of the probability distribution. However, if the null hypothesis is true, then the test statistic has a t distribution and its value would tend to fall in the center of distribution to the left of the critical value where most of the probability is contained. 2. One-tailed test with alternative less than. If the alternative hypothesis H1 such that beta x is greater than C is true, then the value of that t statistic tends to become smaller than usual for the t distribution. We reject the null hypothesis if the test statistic is smaller than the critical value for the level of significance alpha. The rejection rule is to reject the null hypothesis and accept the alternative hypothesis if t is less than or equal to t, bracket open, 1 minus alpha, comma, capital N minus 2, bracket closed, squared. The non-rejection region consists of t statistic values greater than t, bracket opened, alpha, capital N minus 2, bracket closed. When the null hypothesis is true, the probability of obtaining such a t value is 1 minus alpha in bracket, which is chosen to be large. Thus, if t is greater than t, bracket open, alpha, comma, capital N minus 2, bracket closed, then do not reject H0 such that beta x is equal to C. 3. Two-tailed test with alternative not equal to. In a situation where the alternative hypothesis H1 such that beta x is not equal to C is true, then the value of the t statistic tends to become either larger or smaller than usual for the t distribution. In order to get the level of significance with alpha, define the critical value so that the probability of the t statistic falling in either tail is alpha over 2. The left tail critical value is t, bracket open, alpha over 2, comma, capital N minus 2, bracket closed, and the right tail critical value is t, bracket open, 1 minus alpha over 2, comma, capital N minus 2, bracket closed. Reject the null hypothesis that H naught such that beta x is equal to C in favor of the alternative that H1 such that beta x is not equal to C if the test statistic t less than or equal to t, bracket open, alpha over 2, comma, capital N minus 2, bracket closed, or t is greater than or equal to t, bracket opened, 1 minus alpha over 2, comma, capital N minus 2, bracket closed, cube. Since the rejection region consists of portions of the t distribution in the left and right tails, this test is called a two-tailed test. Thus, the rejection rule is that reject the null hypothesis and accept the alternative hypothesis if t is less than or equal to t into bracket alpha over 2, comma, n minus 2, or t is greater than or equal to t into bracket 1 minus alpha over 2, comma, n minus 2. The problem of prediction. On the basis of the consumption function, let us assume we have the following estimates. Y estimator is equal to 30.4151 plus 0.2082 xi, equation 85. Y cap is a true estimator of E, Y I in bracket, corresponding to given xi. Given this, one needs to predict or forecast the future value of y that will correspond to some given level of income x. Two kinds of predictions have been identified. 1. The prediction of the Kodish. Take 2. 1. The prediction of the conditional mean value of y corresponding to a chosen x, say x0, that is, the point on the population regression line itself. And 2. Prediction of an individual y value corresponding to x0. These two predictions are called mean prediction and individual prediction. The mean prediction. To obtain this prediction, let's assume that x is equal to 100, and we intend to predict E into bracket y over x naught is equal to 100. The equation 85 would give the point estimate of this mean prediction as y naught cap is equal to beta 1 cap plus beta 2 cap x naught is equal to 30.4151 plus 0.2082 into bracket 100 is equal to 51.2351, where the y naught cap is the estimator of E into bracket y over x naught. The following is the mechanism by which we can prove that the mean prediction is a best linear unbiased estimator. Blue. Let xi is equal to x naught. The true mean prediction E into bracket y naught over x naught is given as E into bracket y naught over x naught is equal to beta 1 plus beta 2 x naught, equation 86. Then y naught is equal to beta 1 estimator plus beta 2 estimator x naught, equation 87. Taking the expectation given x naught will give us the equation below, because beta 1 estimator and beta 2 estimator are unbiased estimator. Therefore, the equation 88 below, this means that y naught estimator is an unbiased predictor of E into bracket y naught over x naught. Using the property that VAR into bracket A plus B is equal to VAR into bracket A plus VAR into bracket B plus 2 COV into bracket A, comma B, we obtain the equation 89 below. Using the following formula for variances and covariance, follow the equation individual prediction. If we intend to predict an individual y corresponding to y naught is equal to x naught, that is, we want to obtain y naught is equal to beta 1 plus beta 2 x naught plus mu naught, equation 91. We predict this as y naught estimator is equal to beta 1 estimator plus beta 2 estimator x naught, equation 92. The prediction error y naught minus y naught estimator is as written. Thus, the equation below, based on the fact that beta 1 estimator and beta 2 estimator are unbiased, x naught is a fixed number, and E into bracket mu naught is 0 by assumption. Squaring 93 on both sides and taking the expectations, we have the formula below. Using the variance and covariance formulae given earlier and noting variance into bracket mu naught is equal to variance, we obtain the formula below. Reporting the results of regression analysis. There are many ways of reporting the output or result of the regression analysis. Irrespective of the way one has chosen to report his or her results, the most important thing is that it must be clearly reported. For example, the result of the consumption equation is presented as C estimator is equal to 40.5021 plus 0.4082 xi. Standard error is equal to 6.4138 in bracket, 0.0371 in bracket, R squared is equal to 0.19712, equation 95. T is equal to 6.3148 in bracket, 11.0027 in bracket, df is equal to 8, p is equal to 0.0036 in bracket, 0.0000 in bracket. This means that the intercept or outcomes consumption is 40.5021, while the slope marginal propensity to consume, MPC, is 0.4082, which is the rate of consumption from addition level of income. In the result, the first set of parentheses figures in brackets are the estimated standard errors of the regression coefficients. The second set are the estimated t-values, while the third set are the estimated probability value p-value. Therefore, for 8th degree of freedom, the probability of obtaining a t-value of 6.3148 or greater is 0.0036, and the probability of obtaining a t-value of 11.0027 or larger is 0.0000. Thus, the p-values show the exact level of significance of each estimated t-value. The coefficient of determination R-squared shows that over 97% of the changes in the consumption expenditure are explained by the level of income of the consumer. Properties of OLS estimators under the normality assumption. The following are the properties of ordinary least squares estimators: beta 1 estimator, beta 2 estimator, and variance estimator under the normality assumption. 1. They are unbiased. 2. Minimum variance is another property they possess. Combining this with the unbiased property makes them efficient estimators. 3. As the sample size n increases indefinitely, the estimators convert to their true population values. This property is called consistency. 4. Beta 1 estimator is normally distributed with equation 96 and 97, or it can be simply put as the formula below, with the properties of normal distribution of the variable z, that is defined as z is equal to beta 1 estimator minus beta 1 over variance. Equation 98. Z is equal to beta 1 estimator minus beta 1 over variance, which conform with the standardized normal distribution, that is, normal distribution with zero mean and unit is equal to 1 in bracket variance, or Z equivalent n into bracket 0, 1. 5. Beta 2 estimator is normally distributed with the equation below. This can be simply put as the formula which conform with the standardized normal distribution, that is, normal distribution with zero mean and units equal to 1 in bracket variance, or Z is approximated n into bracket 0, 1 bracket closed. 5. Beta 2 estimator is normally distributed with equation 99 and equation 100 below, and also conforms with the standardized normal distribution. 6. n minus 2 in bracket variance estimator over variance is distributed as a x-squared chi-squared distribution with n minus 2 degree of freedom. 7. Beta 1 estimator, beta 2 estimator in bracket are distributed independently of variance estimator. 8. Beta 1 estimator and beta 2 estimator have minimum variance in the entire class of unbiased estimators, whether linear or not. Studies section summary. In this studies section, you explore the confidence interval for regression coefficient and hypothesis testing. You also examine their respective decision rules. This is the end of studies section 6. Thanks for listening.